Alright, so here today we're going to talk about graphing polar curves, and this is super applicable when we're using polar curves in double integrals and things like that, and there's applications of these things to chemistry, physics, things like that. But polar curves are really just an equation. R is a function of theta. That's typically how it's presented anyway. R is a function of theta, and if we look at an example maybe like R equals 2, that's just a fixed radius of 2 no matter what the angle is. So if we cycle through all the possible angles here, so theta can range from 0, so theta equals 0, we're on the x-axis. Theta equals pi over 2, we're up on the y-axis. Theta equals pi, we hit the x-axis again. Theta equals negative 3 pi over 2, or positive 3 pi over 2, we're on the negative y-axis. And I can cycle all the way to 2 pi, and that just gets us a whole circle of radius 2. So we get a whole circle of radius 2 with the polar equation r equals 2. So that's a pretty, I think, fundamental polar curve to look at. Another polar curve we could look at is like something r equals theta, something like that, r equals theta. So the radius is going to get larger as the angles increase. So in that case, we would have something starting out at a radius of 0, but as we get further away, as our angle gets larger, our radius gets larger as well. So that would be a polar curve r equals theta. So as we increase the angle, the radius gets larger, and that would be r equals theta. We could have something similar in that we could have maybe r equals 2 minus 2 cosine. So r equals 2 minus 2 cosine theta, we could have at theta equals 0, we would have r equals 0 because cosine would be 1, so 2 minus 2 would be 1. So r would be 0 at theta equals 0. And then as r gets larger, cosine's getting smaller. So we get further and further out, we get closer and closer to 2 as theta gets close to pi over 2. So then I would have cosine of pi over 2, which is 0. 2 minus 0 would be 2. So our curve should kind of curve out like this. As theta approaches pi, then cosine would approach negative 1, so that'd be 2 minus 2 times negative 1, that'd be positive 4. So the radius there would be 4 when I get close to pi. So at different values of theta, or t, the curve has a different radius. So we can see that here. This was r equals 0, or r equals 0 when theta equals 0, or when t equals 0. And then when theta equals pi over 2, we have a radius of 2. And then the radius gets larger once we get to pi. Then we have 4 for the radius. And then as we get angles larger than pi, our radius starts to get smaller again until it gets back to 0. And that would be what we call a cardioid. So that'd be the cardioid 2 minus 2 cosine t, or 2 minus 2 cosine theta, whatever you want to call your parameter theta. We could also have something like r equals cosine of 2t. Cosine of 2t, if I stick in t equals 0, then I have a value of 1. If I increase that, I go towards the origin. So at pi over 4, my radius would be 0. Cosine of 2 times pi over 4 would be 0. And then we let it run through. We get this nice 4-leaf clover shape. So we'll plot the different points for t as we cycle through. So at different values of t, we have different radius values for r. And that's pretty much what it looks like when we try to graph polar curves. We just look and see what happens to r as t or theta changes. So we'll look at all three at the same time, just for fun. It's kind of mesmerizing. Just do it one time.